So last time we did most of this problem where we had this beam connected to the wall on the left and a roller on the right, and the mass was 100 kilograms. The length is 4 meters. Young's modulus is 100 times 10 to the 9 pascals, and the geometry is such that the area moment of inertia is 1 times 10 to the minus 5th meters to the 4th. And we want to calculate the reactions. And so we did the statics, and from the statics, we went into it hopeful, and maybe we just do the statics and then we have the external loads, but it didn't work out that way. So we got this first equation that said RAY plus RB is equal to 981. And the second equation, that's equation star, 1 star. And then the second equation said MR plus 4RB is equal to 1962. That's equation 2 star. And then when we were done with the statics, we had 2 equations. Well, we really had 3 equations for 4 unknowns. We found out that one of the horizontal forces was 0. The one horizontal force was 0. But this is 2 equations for 3 variables. The variables are RAY, RB, and MR. Well, we can't solve that, so then we went to the deflections. And since there's a fixed joint on the left, we know that the deflection and V prime both have to be 0 when x is equal to 0. And the roller on the right, we know that just the deflection has to be 0, not V prime. And through all of those calculations, we got, so let's say, here's the first one. At x is equal to 0, V prime is equal to 0. So that said 1 over EI times negative 40.875 times 0 cubed. I don't know why I'm doing it this way, but I guess just so you can see what these functions are for the deflection and V prime. Plus RAY over 2 times 0 squared minus MR times 0 plus C1 is equal to 0. So everything inside the brackets is 0, and so we find out that C1 is equal to 0. And then we go to the second boundary condition at x equals 0. So at x equals 0, v has to be equal to 0. And so that one says 1 over EI times the quantity, negative 10.22 times 0 to the fourth, plus RAY over 6 times 0 to the third, minus MR over 2 times 0 squared, plus C1 times 0, C1 is 0 anyways, plus C2 is equal to 0. We like the boundary conditions on the left where x is equal to 0 because usually those just tell us that the constants are equal to 0. And so C2 has to be equal to 0. And so now we can update the deflection function. So the deflection as a function of x is equal to 1 over EI times the quantity negative 10.22 x to the fourth plus RAY over 6 times x cubed minus MR over 2 times x squared. And we've already dealt with, we found out that C1 and C2 are both equal to 0. And so now we've already used these two equations, and they gave us those constants. So those aren't equations that we have sitting around anymore. We've already used them. Okay? And so now our last boundary condition says at x equal to, what's the length? 3? Yes. At x equals 4, the deflection has to be equal to 0. So that says 1 over EI times the quantity, negative 10.22 times 4 to the fourth plus RAY over 6 times 4 to the third minus MR over 2 times 4 squared. And all that has to be equal to 0. You can multiply both sides by EI, and you get, we had two equations that we kept before. Now we have our third equation that says, what's negative 10.22 times 4 to the fourth? 2,216 point, what? 0.32. And that's over here. And then what's 4 to the third over 6? Okay. And that's times RAY. And then minus 8 times MR. And that is our equation 3 star. And so now we have 3 equations for the 3 variables, RAY, RB, and MR. let's calculate that system. So here's our equation 1, equation 2, equation 3. And the variable order, I'll do it in this order. So RAY, RB, MR, and then this is the constant. Our equation 1 star, we have 1 RAY, 1 RB, and the constant is 981. So 1, 1, 981. And our second equation, equation 2 star, I have to clean these up because otherwise you think there's all these time derivatives of everything when you look back. So we have RBs, we have 4. MRs, we have 1, and then 1962. God damn it. 1 MR, 4 RB. 1 MR, 4 RB, and then 1962. There's zeros. And then the last one, RAY, we have 10.6 repeating. MR, we have -8. Constant is 2616.32, and that's 0. And can someone plug that in and tell me what the answer? Okay, so that took a long time, but look at what we did. This is very satisfying if it ever occurred to you during statics that having an over-constrained system doesn't mean that you get a black hole or anything. Like there has to be a way to calculate this stuff, and this is it. So without that roller here, we would have been able to calculate those external loads. Put the roller there, and statics isn't enough. But then if you take into account the way that the deformations occur, you can get those external loads. Let's also calculate the deflection at the middle. I would expect somewhere right around the middle to be the lowest point. Right. 2/3. I don't really know. Yeah, I don't know if it would be 2/3, but you're right. It seems like it should be a little off the middle. But let's, just for a ballpark estimate, let's figure out what that is. Does someone else have a question?
Yeah.
Okay. Well, we can figure out how. We can figure out where it is. We could graph it, or we could, yes, do that thing those math teachers are always telling you to do. So the deflection was equal to, this is a function of x, is equal to 1 over EI. We'll plug that in a second. And then negative 10.22 times x to the 4th. And what do you get? So RAY, can someone tell me what that coefficient is when you plug in RAY? Plug in 613.11. Plus 102.9. And that's x cubed. And then plug in 490.44 for MR. minus 245.22 x squared. So to find the candidates for mins and maxes, dv dx and we're going to set it equal to 0, so we don't care about this. So what do you get? Negative 40.88 x cubed plus 306.57 x squared minus 490.44 x. We're going to set that equal to 0. That is a cubic, but one of the roots is 0. So we have x times negative 40.88 x squared plus 306.57 x minus 490.44 is equal to 0. Can someone find that with anybody who has a TI-89 has a polynomial solver, root finder? So something bigger than 4, we don't care about that. Okay, so let's find the deflection at x equals 2.31. So v at 2.31 is equal to 1 over, what do we have for those values? So 100 times 10 to the 4th, that's 1 times 10 to the 6th. So this is 1 times 10 to the minus 6. And then negative 10.22 times 2.31 to the 4th. Plus 102.19 times 2.31 to the 3rd minus 245.22 times 2.31 squared and what do you get for that? Negative 0.003034. That's in meters, so that's about 1/3 of a millimeter. Pretty great, right? Anybody have any questions about that? That is a softer metal than steel, so it's in the ballpark of the Young's modulus for copper, but it's just a pretty thick cross section or a pretty big area moment of inertia. So the cross section shape makes it pretty resistant to bending. Okay, so I don't want to go through this whole other example, but let's think about what would happen if we also had a fixed joint at the right end. So what would change? Oh, and it's also a very small force. You know, that's a metal bar that the only external force acting on it is its own weight. So, anyways, that's why we had such a small deflection. But what would change with a fixed joint at the right end instead of a roller? Okay, so the boundary conditions we still have a fixed joint at the left, so at x equals 0, we have v equal to 0, and at x equals 0, we have v prime equal to 0. At x equals 4, we have v equals 0. That was there when we had a roller at the right end. But now that we have a fixed joint, there's a new boundary condition. So at x equals 4, v prime also has to be equal to 0. Okay, so all right, so we have one more equation. But how does that work, considering that in the last problem, we already had just enough equations to solve for the variables we had? So what changes so that, does it become overdetermined, or is this something we can solve for? Well, actually, the answer is that when you do the statics, remember that you get a new variable. Yes, the horizontal force is still 0, but now you have a couple because it's a fixed joint. So you get one more variable from the statics. That's the couple on the right. So when you do the statics, the free body diagram now, we have the downward force of 981. Over here you have RA and MA. And now over here you have RB and MB. And actually, there's one thing that I didn't mention there. So we actually gained two new variables, right? We also gained a horizontal force on the right end. So how do we deal with that? It ends up zeroing out, but the way that you would really have to figure out that it zeroes out, because there's like an indeterminacy here. You could have, like, what if this horizontal force was 6 million and this one was 6 million the other way? Well, the way you do that is by also doing the statically indeterminate system for a member in tension or in compression or whatever. And when you do that and require that the length of this beam stays the same, you get that those forces are zero. What? The tension? No. So you go. No. You go. So let's see. What do we have? We have that. So let me just do the tension part. So we have that RAX plus RBX is equal to 0, right? So RAX, that doesn't help. So we'll just leave it like this. And now go to the cut. You have RAX over here, tension over here, so tension is equal to negative RAX. The elongation is equal to EL over EA, so that's negative RAX times 4 over EA, and that has to be equal to 0. So RAX is equal to 0. So RBX is equal to 0. You have a question about that? Okay. There's one more thing I want to say about macroscopic deformations, and it holds for all of the statically indeterminate systems too. What do you do when you have tension or compression and torque and bending moment? Well, the answer is the same answer that it always is in this class. You weren't even listening to what I was asking. You just said free body diagram, and you're right. But no, we're using the superposition principle. That requires that all of these values are small. So small deformation. And what that says is if you want to get the total deformation of this material, calculate. So, calculate your elongation, assuming tension, I guess, and the temp change act alone. And as long as these deformations are small, that'll be basically right. You know, it'll be a good estimate. Then second, calculate the angle of twist, assuming that torque acts alone. And then third, calculate the deflection, assuming that the bending moment acts alone. So all this stuff gets drastically more complicated when you get into large deformations, not to mention that you get into the nonlinear range of materials or even permanent deformation. But as long as you stay in the elastic range and your deformation stays small, we did that example, was it Wednesday, where recently we did an example of a beam deflection where the final answer was like 1/6 of a meter. Now, you can't do calculations like that with these methods, you know. So we did the math right. It just wasn't a loading environment where we can get meaningful results at all. Because yes, so right, exactly. Yep, you're exactly right. Yep. And then right, there's changes in our x-axis doesn't basically go horizontal anymore, so now there's weird things with the moment directions. And what was the, we're making the assumption to start with that that V prime stays close to 0. So if you're getting this big, you know, angle down, that assumption, there's all sorts of things that would have gone wrong at that point. But this one that we just did, where you had less than 1 millimeter of deflection at the middle, you can imagine that that slope stays basically horizontal the whole time. And that's the kind of problem where you can use the superposition principle and it gives good results. Any questions about that? Okay, let's stop. And then, so next time, I think the next thing we're doing is column buckling. And that's the last topic, I believe. So, okay, have a good weekend.